Okay, so let's pick up where we left off. We found the second derivative function. Just to kind of recap the steps here. F prime g minus f g prime. When we got to g prime, though, we really had to consider chain rule, right? Outside derivative times inside derivative. So the outside portion is parentheses squared. The inside portion is natural log of x. So outside derivative becomes 2 parentheses to the first power. And the inside derivative just becomes 1 over x. Okay, so now we're just trying to figure out how to clean this up. Okay. Okay, let me rewrite this in a little bit of a cleaner form. Okay, let me rewrite this. Okay, so y double prime. Okay, so now to help clean this up a bit faster, I like to think of this as 2 separate expressions. Okay, and I want us to take out a common factor or factors that we see between these 2 terms. What do you see as shared that we can easily take out, which will allow us to merge things a little faster? And something else. And 1 over x. Okay, that 2, yeah, I can pull the 1 over x out, and I can pull out natural log of x. Okay, so really, I'm just going to divide those things out. We're going to see things will clean up a little bit for us, a little bit better for us. Okay, so I'll take out the 1 over x. I'll take out natural log of x. And then the leftovers we'll insert into a set of parentheses. Okay, we pull 1 over x. We pull natural log of x. We're left with what for the first term? Just natural log of x. Okay. Okay. If I pull a 1 over x and natural log of x, what's left? All right. Imagine if I just took these 2 away. 2 natural log of x minus 1, right? Okay. All over. So it just speeds up the process to allow us to kind of get this piece cleaned up. Kind of get some things out of the way here. So now that this is factored out, we see a common term that we can remove from our problem. One of the natural log x, this can go away. And I'm also going to try to distribute the negative through so I can combine some like terms. So I'm going to put that above to kind of show what I'm going to try to combine here. So if I distribute that negative 2 through, I get negative 2 natural log of x plus 2. So here's my cleaned up version. Combine like terms, natural log of x minus 2 natural log of x is negative natural log of x. I'll put the 2 out in front here. I'll make this 2 minus natural log of x. If I pull that 1 over x out in front, makes it easier for me to see that, oh, I can just have that x share the same denominator space rather than having to stare at a complex fraction. So I'm going to write this out like this. Okay, so there's my second derivative function. Okay, so take a look. Any questions here? we're going to create our second derivative sine line. So we'll set the numerator equal to 0. We'll set the denominators equal to 0. Look for our critical points. Raise both sides with e as the base. We get x equals e squared. Right. The way I want to solve for x is try to remove that natural log. We know we can undo natural log by involving the inverse function. So raise both sides with e as the base. This goes away. X equals e squared. Okay, so that's one critical point. Next one, we have x by itself. So there's something there as well. X equals 0. And then also the natural log of x cubed equals 0. Cube root both sides. I'm just left with natural log of x equals 0. Okay, when is natural log of x equal to 0? Right, you can use the table or use the graph that you know. Natural log of 1 is equal to 0, or algebraically raise both sides. E is the base. X equals 1. Okay, here's our second derivative sine line. We know to the left of 0, the graph's not going to exist, so we're going to start at 0. Critical points, 1 and e squared. And we're going to choose values in each subinterval to test against the second derivative function, so we can pull information about concavity, right? So I'll test 1/2 here. What's a good number for me to test between 1 and e squared? E, right? Yeah, anytime you take advantage of e, it's going to be really beneficial because we know natural log is going to make it easy for us. Okay, what can we do to the right of e squared? E cubed, yeah. Okay, so one at a time, we'll insert in. Okay, so let's plug in 1/2 first. Okay, what do you know about natural log of 1/2? Okay, what can you tell by looking at this graph? Natural log of 1/2 is going to be what? Negative, right? So probably somewhere around negative like 0.5 or something, okay? So 2 minus negative 0.5, what's that going to give us? Numerator is going to be positive, right? 1/2 is positive. How about natural log of 1/2 cubed? Negative cubed is still going to be what? Negative. So positive over negative is negative. So we know this first interval is going to be concave down. Next up, E. 2 minus natural log of e over e natural log of e cubed. You know the denominator is going to be positive. What's natural log of e going to be? 1. 2 minus 1 is still 1, right? Positive over positive. Concave up. Let's test out e cubed. What can I do with this piece? Anything to make it a little bit easier to interpret? What can I do with natural log of e to the third power? Yeah, move that exponent down in front, right? Because it's part of a log property. You know the denominator is all positive, right? So there's no issues there. Okay. What's natural log of e? 1, right? What's 2 minus 3? Negative, right? So negative over positive is negative. So concave down. Okay, does that make sense? Okay. We see intervals of concave up, we see intervals of concave down. Where do you think we have points of inflection? Okay, let's test that out, right? I mean, we do see a change in signs, so let's just see what happens. Point of inflection, 1, and e squared. So how could we find the actual physical points? Plug back into the original function, right? Okay, let's see what happens here. If I plug 1 into the original function, what am I going to get? Which means undefined. That means this point doesn't exist. If a point doesn't exist, then it can't be a point of inflection, right? That means that there's a vertical asymptote here. There's a change in concavity, but that asymptote is there. It's not enough for us to call that point of inflection, so there's none. Okay, let's test out e squared. There's a change in sign, so we want to see if that point exists here. So we enter e squared in for x. Okay, so how can I clean this expression up? What's natural log of e squared? Natural log of e is 1. You can make that go away. So my y value is just e squared over 2, right? Okay, let me pick out some problems from worksheet number 3. So you guys can turn to page 6. Okay, page 6 in your test review packet. The position of the particle is moving along the x-axis given by x of t. Write an expression for the velocity at any given time. So that just means we got to find the derivative. We can apply the rule for e to the u. E to the u times u prime. Let me try that. Keep the 4/3. E to the u becomes e to the u times u prime. And then 8t becomes just 8. Do a little bit of cleanup. The 3's can be taken out. Okay, acceleration. Again, e to the u becomes e to the u times u prime. The 4 is going to stay. And then the 8 goes away. Put the coefficients together. Okay, for part C, for what values of t is the particle at rest? How do we approach that? Yeah, velocity equal to 0, right? Rest means motionless. Motionless means velocity 0. Okay, e to the 3t equals 2. How do we get that? How do we get that? Get to that 3t so that I can solve for t? All right. Prefer to bring it down, but what should we do if we want to bring it down? Yeah, we got to have part of a log expression, right? Because once we're inside a log expression, exponents can be free to move. 3t comes down in front. Natural log of e we know just is 1, so that goes away. Solve for t. Divide both sides by 3. Okay, for D and E, we're just evaluating velocity and acceleration. So we just insert 3 into both velocity and acceleration function and find those values. Okay. Part F. At t equals 3, the velocity of the particle is increasing or decreasing. Okay, how do we go about interpreting this here? What do we look at?
We look at if acceleration and velocity are at the same time.
Look at F and G. One is velocity increasing, the other is whether the speed is increasing or decreasing. What's the difference? I think what you're describing there is speed increasing, decreasing. Yeah. Okay.
It's acceleration.
So just acceleration, right? I know you see the word velocity, you want to use velocity, but the increase, decrease is kind of changing how how they're defining it, right? Increase, decrease means it's the rate of change of velocity. Rate of change of velocity isn't velocity. Rate of change of velocity is actually acceleration. So we're just going to look at acceleration. Acceleration is positive or negative? Positive, therefore, velocity is increasing, okay? Now for G, to test whether speed of the particle is increasing or decreasing, here we do what? Now we compare signs, right? Increasing would be where the signs are what? The same, right? Either they're both positive or both negative. But if one is positive and the other is negative, right? Doesn't matter which one is which, but if there's opposite signs, then speed is going to be decreasing. So here, these are both positive, right? Okay, questions? All right, let's look at number 4. Find dy dx of natural log of yx equals y squared minus x cubed minus e. We want to find the derivative. There's two things that I want you guys to point out. What process is involved here? Implicit, all right? You see y's mixed into the equation here, so implicit, definitely. What else? What do you mean? Are you talking about this natural log of xy or natural log of yx? Okay, so what can we do with that natural log of yx? Yeah. Yeah, so we don't want to do derivative just yet. We want to expand so that we're not having to stare at such a messy u value, right? We'd prefer not to have a u value being y times x. So I guess we could have done product rule within natural log, but why not just expand, especially if we have that ability to with natural log. So we want to go through log expansion. So that's actually what we want to do first. We want to do that cleanup before we consider our derivative rules. Okay, so natural log of AB can be expanded into natural log of A plus natural log of B. Product property. So now we have all these singular terms. We can just apply the derivative rule for each term, and then tack on dy dx whenever we come across any y derivatives, right? So we got u prime over u for the first two terms. We have power rule for the next two terms. Okay. First term, natural log of y, what does that become? Okay, 1 over y, dy dx. Natural log of x becomes 1 over x dy dx. Sorry, just 1 over x, right? There's no dy dx for the x term. Equals y squared. What does that become? 2y. Just 2y? dy dx. X cubed. 3x squared. What about e? 0. Okay. E is not the same thing as e to the x. If it was e to the x, we'll make it e to the x times 1. But e is just a number. It's like 2.7. So constant will just go away. You don't have to put a 0 there. I just want to show that we did take care of that e, and that e is going to go away. Okay, so the hard part is done. We have the derivative. The rest is just trying to rearrange and get that dy dx by itself. Factor out the dy dx. Now let's just divide the parentheses over. Okay, any questions here? Okay, if you guys can get out a sheet of paper, I want us just to kind of hit some of the kind of like the smaller problems here. I want to do a derivative inverse at a point. I want to do a log differentiation. Maybe do a log expansion problem. Okay, so let's start with a derivative inverse at a point. You guys can copy this problem down here. Yeah, just grab it from the top of the shelf. Okay, so derivative of inverse at a point. So the thing that we have to understand is that there's kind of an established relationship between a function and the inverse. And that relationship, order pairs wise, is that whatever order pair sits on the inverse function is going to be the flipped version on the original function. So if you see an x for inverse, it's going to be y for the original and vice versa. Okay. So the first thing to recognize is that this 6, even though the 6 is the x value of the inverse, for our purposes, is going to be the what of the function, the y value. Okay, so that's the first thing we have to make sure we understand. If we start inserting this 6 in for the x, it's going to throw everything off because these are not, right? These are related, but these are not the same function. So we need to understand that this 6 is going to go in for that y slot there. Okay, I like to create a table to kind of help map my progress here. So the top portion gives me information about order pairs. The bottom portion gives me information to the slope relationship between the function and its inverse. So if I want to find the derivative of f inverse at 6, that's my final goal. But I also know that the order pairs is going to be flip-flop. Right now, I only have the y value of the original function. I'm going to have to work backwards to figure out what x value to use so that I can find the slope. Once I find the slope, I can turn around and figure out the slope of the inverse. So we know the 6 is going to go in for the y. Okay, we know that this is not going to be factorable. We'll bring everything over to one side, set equal to 0. These, the number will be easy to find. You'll just test numbers around 0, and eventually you're going to get there. So let's test some numbers here. So if x is equal to 0, is that going to work? 0 minus 0 minus 4, is that equal to 0? Not going to work. Okay, so let's test 1. 1 minus 5 minus 4. Will that work? Negative 4 minus 4 doesn't work, right? How about negative 1? Negative 1 plus 5 is 4. 4 minus 4 is 0. Yes, this works. Okay, so after a series of guess and checks, we're able to confirm that the order pair that kind of fills out that relationship is the inverse function has order pair 6, negative 1, but the original function has order pair negative 1, 6. But now that we have the x value for the function, we can move towards finding the derivative, which will get us the slope, and then we can let that number lead us to our answer. Okay, so I need to find f prime of negative 1. To find f prime of negative 1, I first have to find what? Derivative. Okay, so what's the derivative here? F prime of negative 1. What does this get us? Slope is what? Negative 2. So if we know the slope of the original function, can we figure out the slope of the inverse? What's that numeric relationship going to be? Good. Just flip the number. Do not change the sign. Okay. Any questions about the process there? Okay. Whatever number they give you, put it in for the y slot, guess and check your way until you find the x. Then find the derivative of the function, insert that x value that you just found, Take that slope number, flip it, and that's going to be your slope that you're targeting. Any questions? Okay. Let's do a okay, are we good here? All right. I did this in the help session, but I think it's good for us to go over here. Copy this problem down. First things first, let's go ahead and rewrite this problem so we can see this maybe a little more clearly. How can we rewrite this problem? Yeah, to the power of 1/7. I can merge the 1/7 and x and make it 1/7 x, right, or x over 7. Now, look at what we have here. What is involved here for this type of problem? Can we do power rule? Can we do exponential rule? Is this chain rule? All right, so we need to realize is that there is no rule that can handle this problem, okay? Because you got a variable base, and you have the variable exponent. We don't have a rule for variable raised to variable. So what can we do so that we can get this to look like something else? You guys remember? Is there anything that we can do to maybe allow that exponent to come down? Yeah, log differentiation, right? This is where we introduce logs into the problem to force properties to allow for us to kind of move forward, right? Because right now we're stuck. We don't have anything that can, we don't have any rules that can handle this problem. Okay, so we take the natural log of both sides. First, I rewrote it as 1/7 x. Once the natural log is in play, what can we be free to do here? Exponent can rock down to the front. Once it comes down, then we can consider our derivative rules. Left side is implicit, 1 over y dy dx. The right side, we need to recognize this as product rule, right? There's 1/7 x. That's a separate expression from natural log of x squared minus natural log of x. Both are outside of each other. They're being multiplied. We got to go through product rule. Okay, so now f prime g plus f g prime. Okay, what's f prime? G function, no changes. Back to f. And then g prime. Okay, let's talk about g prime here. Our g function is this natural log of x squared minus natural log of x. Okay, I want you to understand that this piece right here, that's the u value, right? And we're trying to force it into a, or not force, we're going to turn it into a derivative, so u prime over u. So it's going to have to take on this form in this space right here. So if we just look at the g function here, if we understand that this parentheses is u value, we'll find the derivative one piece at a time, right? What's x squared's derivative? 2x. What's natural log of x's derivative? 1 over x. So they're all going to kind of be next to each other to represent the derivative of that parentheses, right? The parentheses has multiple terms in it. We took care of each derivative. All over. Yeah, all over what's inside the parentheses. Okay, does that make sense? That we're taking the derivative of this messy problem or messier problem, so you have to kind of, it feels like a little bit more going on here. Okay, so the calculus is done. Now we just have to try to get dy dx by itself. We'll move that y over to the right side. We'll have a replacement for y. And then this is going to do a little bit more cleanup, but the majority of our work is done. I'll distribute the x through and the 7 to the bottom. And finally, the y back in terms of x, or the original problem. Okay, any questions here? All right, let's do one more here. All right, copy this down. Maybe this looks a little more intimidating because you have log base 5, but just pretend like it's natural log and start the problem thinking it's natural log, and then at the end, we can adjust for the fact that it's log base 5. What do we want to do first before we find the derivative? Log properties, right? Expand out all the way so that we're not having to deal with such a messy u value. So as a reminder, any term that's left in the numerator is part of a positive log, natural log. Anything in the denominator is part of a negative log. So if I have log or natural log of a over bc, that expands to be natural log of a minus natural log of b minus natural log of c. Okay, so just as a reminder, that's how, hopefully you're able to see that there are kind of 3 terms, and we want to kind of break them down into separate chunks. So first things first, we just expand. using a combination of quotient and product property. We can also begin to convert some of these radicals to rational exponents, but then also consider what we can do after that. Is there anything else we can do to clean this up? All right. Prefer not to do derivative just yet, right? What else can we do? Yeah, this is more important. The 1/2 needs to come down. This x squared, it's up to you. I mean, the derivative is not difficult, so you can either bring that 2 down or just leave it there and just do u prime over u. But this we want to bring down. Otherwise, we're stuck in having to do a chain rule. Okay. So now we're ready. All right, u prime over u for every term. But this first term here, what is this here? This is a what? It's constant. There's no variables here. There's no x's here, right? So that's just going to turn into what? 0, right? I mean, you could go through the rule for our derivative, but it's not going to amount to anything, right? Okay, so u prime over u. I'm sorry, for log base a of u, it's u prime over u, but with a little bit of conversion extra, right? So 1 over ln of a times u prime over u. Okay, so test tomorrow, help session tomorrow morning, 7:15. I have a morning review worksheet that's already available if you want to work through that along with the key. I recorded a video from last year, so you can definitely watch that if you want tonight. But you can join tomorrow for the help session. Make sure you memorize your derivative rules. No calculators. Okay. Look through the rest of your packet. I have some helpful hints and notes that hopefully you'll find useful.